Swayam Prabha. Digital India. Educated India.
Hello everyone. So in the last session we have discussed the comb sorter and different parameters which we get from the comb sorter diagram, and now we will continue with the comb sorter, understanding the basic concept of drawing the comb sorter. So let us discuss this example. Here the question is that to draw a typical comb sorter diagram of 70-30 polyester cotton blended fibrous mass. So here it's a basically, although it's a theoretical part, we normally don't draw comb sorter of 70-30 polyester cotton, but if we want to understand the detailed concept of comb sorter, we must try to learn the tech tricks of this. Now, if we were asked to draw comb sorter diagram of 100% polyester fiber, we have seen that comb sorter diagram of cotton, so the length from the higher length to lower length we distribute, this is length, and polyester means we consider polyester, it's a cut length of say length of say L equal to say 51 millimeter, and here all the fibers are of equal length, and this 51 mm, so 10, 20, 30, 40, 50, 60, 70 millimeter length. So here our length is 51 mm. So you have the fibers of equal length. Now in comb sorter we take the maximum length here. The one fiber we are taking left. The next fiber, when we are trying to take, we found the next fiber is of having also same length. So in this way we are arranging the fibers of equal length. So this is the comb sorter diagram of a polyester, 100% polyester of 51 mm cut length. So for man-made fibers with equal cut length, the comb sorter shape of the comb sorter is rectangular shape, and for cotton or a natural fiber with a variable length, it's typically S shaped, and this is the rectangular shape. Now with this concept we will try to solve the present problem. So what are the conditions given? Now consider the maximum length of cotton and cut length of polyester are 35 and 40 millimeter of respectively. So, maximum length of cotton is 35 mm and 40 millimeter is the cut length of polyester, and 70/30 we are talking about the shape of the comb sorter. So, the mass proportion we will try to do, it's approximate. Okay. Now, imagine these fibers are mixed. So, polyester and cotton are mixed in a mass. So, polyester, let us try to see, draw. These are the polyester fibers. All are 40 mm length. And the cotton is shown in purple color with the maximum length is 35 mm. This is a mixture. Now we want to draw the comb sorter diagram of these fibers. If you see, the comb sorter diagram, so this is showing y axis is L, this is frequency, the cut length of polyester fiber is 40 mm, which is longer than the maximum length of cotton. So, during the comb sorter process, we will first sort the polyester fibers. So, polyester fibers will be taken. So, as we have seen, all the polyester fibers are taken. All the polyester fibers are taken because the maximum length of cotton is less than that. After selecting all the polyester fibers, in this mass only the cotton will remain. We have already taken the polyester fiber, and is here the condition is a 35 mm is the, so 4, 3, 10, 20, 30, 40, 50 mm length. Now 35 mm, this is a 35 millimeter maximum. So, the cotton portion will get started from this point 35, and then all the cotton fibers will have normal sorter diagram. These are the cotton fibers, all cotton fibers. So, typical shape of the 70/30. So, this is this its content is approximately 70%, here it will be 30%. That we can adjust. Okay. And our next problem is that consider the maximum length of cotton and cut length of polyester are 35 mm and 30 mm. Earlier case the cut length was 40 mm and here cut length of 30 mm, which is less than the maximum length of cotton. Now, if we draw separately for cotton, this is let me draw once again. So, the length is 10, 20, 30, 40, 10, 20, 30, 40 millimeter. The cut length of polyester is 30 mm. So, this is the shorter diagram of polyester, and if we want to draw the shorter diagram of cotton with the 35 millimeter maximum length, so this will be 35. So, these are the separate curve. Separately, this is for cotton, this is for polyester. Now, when we draw the Comstock diagram of blend, the system will be different. The shape will be entirely different. Ten, 20, 30, 40, so this is 35. Now, the maximum length here it's 35, which is more than the cut length of polyester. So, initially when we draw from the mass, we will start drawing the cotton till the length cut length of polyester reaches. This is the and then polyester portion comes. This is a polyester. All the polyester fibers are there at the midpoint. Middle of this, and here the longer cotton fibers, longer than 30 mm. After that, remaining cotton fibers are less than 30 mm. These are the cotton. Cotton fiber. Effectively, what is happening? This cotton diagram is broken into two parts. So, longer fibers are going in the left side and shorter fibers are in the right side of the polyester component. So, in this way we can plot the typical shorter diagram of any blended fibers. Let us try to do another problem. Here it is a tertiary blend. So, cotton, polyester and viscose fibers are there. So, typical comb shorter diagram we have to draw where 50% cotton, 25% polyester and 25% viscose are blended, where the maximum length of cotton is 35 mm, cut length of polyester is 40 mm and cut length of viscose is 30 mm. So, again try to draw the individual curve. Ten, 20, 30, 40. Viscose, if we draw, it is a 30 mm. This is the viscose curve, individual viscose. Then individual polyester. Polyester is a 40 mm cut length. Polyester. Now, cotton with maximum length of cotton is 35 mm. So, this is 35. So, we can draw now we have to mix it. We have to mix, that means the polyester length is higher than the maximum length of cotton and the cut length of viscose, which will, that means which will be taken at the left part. And like earlier numerical, the cotton will be distributed with the viscose fiber. So, let us see the shape. This is the shape we will be getting, where 25% polyester, which is represented by A, is taken at the left zone, and cotton is distributed into two parts, B and C, B and D, and in between viscose is inserted. So, we will get the clear separation of all these fibers. Now, next method is that after the comb shorter, the next method is single fiber length measurement, which is actually tedious method. For industry purpose, we normally don't measure the fiber length in the industry, but for some special occasion, just to for research study, we do the single fiber length measurement, like fiber length breakage, damaged fiber length during the yarn breakage, some special study, we can measure the fiber length in the single form. So, single fiber length for man-made fiber we don't need to measure because we know the cut length. For fibers of variable length like cotton, we can take. So, each fibers we take separately and straighten it. Length of each fibers are noted. The length is noted. This method is tedious and time consuming. So, we can measure, but it is a tedious method. So, we do not use in the industry, but when we have a small quantity of fiber, suppose this is a very small quantity of fibers available, and this fibers we cannot use any existing method, there in that case we have to go for the single fiber length. Few fibers are available. So, in weight basis we have already discussed. So, from the shorter diagram we take the length group, okay. So, in this different length group we measure. You can see here, as we have discussed, that length group L1 we take the weight of this, and length group 2 L2, this is the weight. So, here the weight is W1, in this zone weight is W2, W3, in this way we can take the weight at different length group, and then we measure the mean length. So, here length group, so W1 L1 plus W2 L2 W3 L3 plus W4 L4 divided by W1 plus total weight. In this way we will get the mean length. Let us try to solve one numerical. The masses of cotton fiber are 5 milligram, 2 milligram and 1 milligram in the length groups of 30 millimeter, 20 millimeter and 10 millimeter. So, from earlier diagram, so this is the length group of 30 mm, 30 mm length group. Then this is the 20 mm length group, and this is the 10 mm length group. Here 30 mm length group and weight is 5 milligram. 20 length group, weight is 2 milligram, and 10 length group 1 milligram. So we have to calculate the mean length. So mean length we will calculate, it's a very simple, 30 multiplied by 5, okay, W into L, W1 L1, W2 L2, so 20 multiplied by 2 plus 10 multiplied by 1 divided by the total mass. So 5 plus 2 plus 1. So in this way we can calculate the mean length based on okay, this will not, this will be 8, sorry, 5 plus 2 plus 1. So ultimately this will become 22 multiplied by say 9 by 8, it will be 20, approximately 25. It's a 25, not the 22, it will be 25 if we calculate. So in this way we can calculate the mean length based on the mass. Now next method is the clamp tuft method. This clamp tuft method is used mainly to measure the fiber length from the sliver. So during process, so after during carding or draw frame, we get the fibers in sliver form and we have to measure the fiber length. Here we get only the mean length of the fiber, approximate mean length, by clamp tuft method. Here this is the tuft with of parallel fibers. So we can also measure from the fiber tuft also, but we have to actually make it parallel. So here this fiber parallel fiber tuft is first, it's a clamped by a clamp of certain width. This is the fiber mass. What we are doing, we are clamping the fibers and you just remove the protruding fibers which is not gripped, and after that we remove further by combing. After combing we are removing all the fibers which are not gripped. Now here all the fibers are gripped by the clamp, okay, and this projected fibers are then cut. So clamped fibers are combed to remove the loose ungripped fiber. So all the ungripped fibers are removed, okay. We are combing. After combing, the protruding fibers are, so this is after combing. Now these protruding fibers are cut by the knife. So this is say, and then weight. So W, this is, you are taking the weight of this fiber. So this is say M1 and other side say it's M2, okay. So total protruding fibers are M equal to M1 plus M2, total protruding fibers you are cutting, and after that we have to open this clamp and we will measure the fibers, the weight of the fibers which is within the clamp, MC, clamped fiber. M is the and within this it is MC is the fibers which are within the clamp. So total weight of fiber will be M plus MC. This is the total weight of fiber. So total mass of fiber, mass of uncut fibers, mass of clamped fibers and mass of cut fibers, total mass we have got. That is, then we just use this simple equation. So mean length, which is actually proportional to the width of the clamp, represent the width of the clamp, and total mass of tuft top, total mass by mass of tuft, clamp top. So with that ratio we can calculate the mean length. So mean length is calculated here. This is based on the mass, so that's we call it as mass biased length. So width is known, which is constant. So mass biased fiber length we can calculate. So width of the clamp by the mass of the clamp tuft, which actually shows the, which is actually eliminating the effect of the density of the fiber. So fiber density we are eliminating with that ratio, so that the mean length of the fiber is the actually proportional to the total clamped length, weight of the fiber. With this ratio we can calculate. So mean fiber length is proportional to the total mass of the fiber. Now suppose, now let us see two fibers are clamped, two different types of fibers are clamped. This is the clamp, okay. Now fiber 1, they are arranged in the same fashion, number of fibers are arranged. So number of fibers say X. Now another fiber, the X number of fibers we are clamping. And considering the fibers are of same micronear, same number of fibers are we are. So in these two cases, width is constant and mass of clamped fibers will also be constant, same. In these two cases, mass of clamped fibers will be same. Only difference is that this protruding fibers, which is actually affecting the total combed mass. So, here in fiber Y, in case of Y, the protruding mass will be higher, so total mass of the fibers will be higher. So, it is that is indicating the mean length of fiber. Now, let us try to solve one numerical here. So, mass of cut edge of fibers and clamped fibers are 20 gram and 5 gram respectively. Width of the clamp is 10 millimeter, then mean length of the fiber will be, so this same relationship we will be using here. So, you can see here total mass, clamped mass and edge fiber. So, total mass will be 17 gram and width is known. Width of the clamp is 10 millimeter. So, this is 10 millimeter. Clamped mass is 5 gram. Okay. Total mass is 17 gram. So, all this data we are having, so we can calculate the mean length. So, it is 34 mm is the mean length. So, this is weight basis mean length. Next, most important part here is the fibrogram. So, to get fibrogram, we use the instrument which is known as fibrograph technique, which works on optoelectronic method. So, here we produce the fibers in length biased manner. So, length biased manner we have discussed earlier. So, when we take the fibers from the surface, we pick the fiber in the length biased fashion, where this we have discussed, the proportion in the sample get changed, which is different from the population, and it is changed in this fashion. Like, let us take example of 3 different fiber length of equal proportion, 1:1, 1:1, all 3 are of 15%, but here as the longer fibers are selected preferentially, so it will become 1:2:3 proportion. In this proportion we will select the fibers. Now, considering the fiber, so the removal of length bias sample will change the proportion of fiber in the remaining bulk, that we have already discussed. Now, here when we select fiber from the bulk, the longer fibers are selected preferentially because of the surface presence of the longer fibers are more. So, the chances of crossing the lines A and B is proportional to their length. So, like one fiber is there, this is one fiber, small fiber, this small. So, if you see the longer fiber will have higher probability of crossing the line. That means these lines A and B are the gripping point, that they will be picked. So crossing the points, then the longer fibers will have preferentially selected, and which will result the length biased sample. So we prepare using the Fibro sampling technique. Now let us consider all the fibers are of equal length. All the fibers are of equal length. So this all of equal length. Now in the Fibro sampler clamp, the fibers are picked randomly at any point. That's the condition. The fiber is caught on the comb in proportional to their length. So longer fiber will have higher probability, and the point where it is caught is at random along its length. Now in this condition, here in this picture, we are eliminating the first assumption. That means longer fibers and shorter fibers are not there. All the fibers are of equal length. So only we are now dealing with the assumption 2. That is, the fibers are picked randomly at any point along the length. Here we have 6 fibers of equal length and they have been selected. All the 6 have been selected. But as per the second condition, they are picked at different point, like 1, 2, 3, 4, 5, 6 fibers. You can see fiber 3 is picked approximately at the center, fiber 4 at the edge, end point, and 1, 2, 5, 6 they are selected at different point. Now the system is like that. Consider this is a fiber, this is single fiber, say fiber, say 1, fiber 1 here. Now it is picked in this fashion by the clamp, and what will happen? It's a flexible one, and the clamp is there, and this fiber will form a fold. It's a loop. This is a loop. Now if you consider the third fiber, number 3, at the center, this will form a loop like this, where equal, both the ends are equal. So in this way, if we arrange, so fiber 1 is arranged in this fashion, fiber 2, fiber 3, fiber 4, fiber 5 and 6. They are forming a loop in that. Now this clamp is ready for the scanning. Ready for scanning. Now let me draw this clamp in different fashion. Let me take the longest fiber first at the top. We are just rearranging, and each fiber end projection will be treated as a single fiber. here number 1 fiber will be treated as 2 fibers as far as the fibrogram is concerned. Okay. So in the fibrograph machine, the scanning will be there, but in the fibrogram, when we are getting, this will be treated as 2 fibers. But if you consider fiber 4 as it's peaked at the edge, it will be treated as a single fiber. Though if you tell which one is more accurate, comb sorter or fibrogram, comb sorter is very accurate, where we take the actual length of the fiber. But here we are doing 2 wrong things. One is we are selecting the fibers in length biased fashion and with the certain assumptions are there, length biased fashion, and we are picking the fibers not at the edge end point. We are not able to pick the fiber. Suppose this is a fiber, we are not able to, there is no mechanism we are able to pick the fiber. But if you want automation, if you want very quick measurement, comb sorter is not the method. It will take time. I want some fiber related parameters. So what the normal practice is that, let us take length bias sample, let us have some assumptions, let us test it, and we will generate some separate entirely different parameters to express the length characteristics, which will be standardized and which has been standardized and accepted. Now, what we are discussing, let us now try to arrange it. So, first fiber which is coming at the top, okay, just we will arrange in like a sorter diagram. Let us arrange in like sorter diagram. This is the length and this is fibers, number of fibers, frequency. Number 4 fibers we are arranging at the leftmost point. Number 4 fiber. Next fiber will be, which is number 6, this part. This is part 1, this is part 2. 1, 2, 1, 1, 2, 1, 2, 1, 2 in this fashion. So 6, 1 we are taking, which is less than the 4, definitely. Next fiber will be say 2, longer part. In this way, if you go on doing it, you will get a curve like this. Which is triangular shape. What is this? When you are scanning it, we are scanning it, large number of fibers will be here, then gradually the density will reduce. So large number of fibers means large frequency number of fibers here with the span length, scanning length say 1 millimeter, then 2 millimeter, 3 millimeter we are going, and frequency is reducing with the span length. We are increasing the span length, but frequency is reducing gradually. Frequency is reducing, and this is the typical shape of cut fiber, fibers of equal length. And if we try to take the incorporate another complexity, which is length for cotton, we can imagine, this is the for simple understanding, but we can imagine what will happen to cotton, and for cotton we will get a typical shape like this. This is the cotton where length variation is there. We have taken the, and here the thing, another advantage in cotton is that all the folding is taking place, and in the same time, at the same time we are taking the longer fibers. Longer fibers are preferentially taken, and also the folding is taking place. So this two gets superimposed, and finally we get this type of shape. So let us see the fibrograph method. So optical method of measuring the density of fiber along the length. So here the density of fibers will be measured along the length. We have produced tuft. So here you can see, here at when you start at the grip point, the density of fiber is maximum. Gradually if we move towards the end, the density is reducing, and that is scanned by the scanner, photoelectric scanner. Maybe some slit laser beam can be passed, and fibers are prepared by fibro sampler, as I have mentioned, in the length biased fashion. So this is the clamp of cotton fiber of different length, and we have produced the loop form, and the photo sensor is sensing, and it is as it is moving, photo sensor is moving, it's giving a plot of proportion of fiber in y axis and length spanned in x axis. So at the starting point where 100% fibers are there at the point of clamp, this is called fibrogram. The diagram which is we obtain from fibrograph is the instrument, and fibrogram is the plot. Now we can see the animation. Just see the when the scanning is going on, at the leftmost point the 100% fiber, whatever the maximum density, we call it as 100%, as the term is 100%, Then as we go towards the right side, gradually the number of fibers reduces and this plot is generated. So where the density number of fibers are 50% of the initial fiber, we call it as the length which is spanned, which call it as the 50% span length. And we continue. Suppose we have 1000 fibers initially. So at 50% span length, that after moving to that length, 500 fibers will be there, which will be longer than that length. And another parameter, length parameter, which we get, which is called 2.5% span length, that is the length beyond which only 25 fibers will be there out of 1000 fibers. Okay, so that's the concept of the fibrogram. We get these parameters as we have already discussed. The spanning is taking place. So if there are say 1000 fibers are there, as I have mentioned, so within this length AB, so at the point of B there will be its 500 fibers will be there. So this length is called 50% span length, and that means 500 fibers are beyond this length, more than this length, and 25 fibers are more than this length, that is 2.5% of the fiber. Okay. Now fibrogram, and this is the typical fibrogram we have already discussed. Now how to analyze this fibrogram? So this is the 50% span length, this is one parameter we get. 2.5% parameter we get this 2.5% span length. Apart from this, we get many other parameters, and variability we can calculate. So which is one parameter is uniformity ratio, which is the ratio of 50% span length by 2.5% span length, and we can express also in terms of percent. Now let us try to see the analysis. Now fibrogram is drawn as we have seen earlier. So by scanning, now the length L1 dash, which is 50% span length as we have mentioned, and then the 2.5% span length we get here. So from there 2.5% and 50% span length, we can calculate the uniformity ratio. Okay, so L2 dash is a 2.5%. And then what we have to do? We draw a tangent on the fibrograph a tangent from the 100% point, the green line, which is intersecting the x-axis at A point. So OA is known as the mean length, which is different from the mean length which we have calculated in by the other methods. Here we can call it as mean length in fibrogram, and Again we draw a tangent from 50% point, and which is intersecting the x-axis at B point. So OB is called the upper half mill length. So upper half mill length OB, and OA is the mill length as per the fibrogram. Okay, and then we can calculate the uniformity ratio based on the span length, and uniformity index is calculated based on the mill length and upper half mill length. The ratio of mill length and upper half mill length is the uniformity index. Okay, so typically the relationship between uniformity ratio and uniformity index is 1.8 times typical for typical cotton, 8 times to that of uniformity ratio, and typical range of uniformity ratio is 40 to 50% for, and it cannot be more than 50% typically, and maximum is for that we will calculate, we will see, and less than 40% is a high variability, poor quality, and typical value of uniformity index for cotton is 75 to 80%. Okay, so now 2.5% by definition, the 2.5% span length is defined as the length of fiber at which only 2.5 fibers of the fibers which are longer than that. Okay, and there are some relationship, 2.5% length is close to the upper half mill length as we have seen. So if we, this is 2.5%, and if we draw the tangent from the 50% point, you will see this will be close to the upper half mill length. Okay, and 50% span length, as we have only 50% of fibers are longer than that particular length. So uniformity ratio is calculated by the, it's a ratio of 50% span length by 2.5% span length, and that we have already discussed, 2.5% span length, and this uniformity, the typical values of uniformity ratio is that 48% and above should be very high uniformity index. So 48%, if you get the uniformity index, that means the fiber is very good, and below 40 is lower, very high variability, that means very low quality. And upper half mill length, we have already discussed the upper half mill length. Okay, the average length of longer half of the fiber. Uniformity index is the ratio of mill length by, mill length means mill length measured by fibrogram. Now uniformity index, and this is a more than 85, very high, so it will be typically 75 to 85 in that range uniformity index, and typical cotton we get 80 to 82, okay, around 80, so that we get, so 85 is very good. Now we will try to understand the, with this superimposition, we will try to understand that how the comb sorter diagram and fibrogram are originating, and what are their implications, and all this we will discuss in the next session. Till then, thank you.